Welcome to next lecture. So today we'll go for the last video you have learned regarding the Illemnites and Perovskites magnetic property. Okay, so today we'll learn little bit more of this Illemnites. This Illemnites is nothing but Illemnite. Okay, this is nothing but black mineral with black mineral. Okay, and it has the mineral with the submetallic to metallic luster, so it is having some metallic luster. Okay, so this is what very important. And if you see the physical property of this ilmenite, they are having the classified into the oxides mineral. Okay, oxide minerals crystal system, and they hexagonal type. Okay, hexagonal crystal system, hexagonal. Okay, mineral crystal system. And the main use of this is it's a primary ore of titanium. This is very much important. Okay, and the source of iron, okay, used to make the titanium dioxide, TiO2. So this is important. Okay, found in mostly igneous rocks, ilmenite. Okay, sedimentary rocks. So in this, or sediments, so in this we can find this ilmenite. Okay, so it is black iron, also titanium oxide. We say it is a black iron titanium oxide, TiO2. Okay, so this if you see the chemical composition of this, so it is FeTiO3. So iron, okay, black iron titanium oxide, FeTiO3. This is the composition, how it is ilmenite are found. And it's a primary ore of the titanium, and it is needed to make some variety of high performance alloys. So it is used to make high performance alloys. Okay, and it is used to manufacture, mainly it is your titanium dioxide. Okay, this is mainly used. And why this titanium dioxide is used? It is used as an important pigment. Okay, titanium dioxide as an important pigment, white pigment, whitening or polishing abrasives. It is used for whitening or polishing abrasives. Okay, abrasives. So this is what about the titanium, very costly. Okay, so extraction of titanium oxide and using the application is very useful marketing nowadays. Okay, and this ilmenite forms usually they form by cool slow cooling the magma chambers, magma chamber. Okay, this is a geological term. So magma chamber. So and where the slow cooling will takes place, and then the concentrated process is done, that is magmatic segregation magmatic segregation is done. Okay, this is all geological term. And then you can see that this has been extracted, titanium dioxide. Okay, or ilmenite has been extracted. Okay, and this is found underground, and it takes centuries to cool. So that's why they are very costly and very difficult to extract also. And as it cools, the crystals of ilmenite will begin forming at specific temperature. So that is what ilmenite exist in the nature. Okay, and these ilmenite, they have high resistance to weathering. They have high resistance to weathering, so they will not weather easily. Okay, breaking and all weathering, small particles. So they have high resistance, they have high specific gravity. Okay, ilmenite do have high specific gravity and accumulate as a heavy mineral sands, black in color. Heavy mineral sand, we call it black mineral also, some they call it. Okay, a solid solution series exists between ilmenites. Okay, solid solution also is existing, that is FeTiO3. And one more is there, MgTiO3. See here, magnesium is been introduced in place of iron, and they become solid solution if we mix both. Okay, and this, when magnesium TiO3 is there, it is called as gikilite. Geikeilit, gikilite. It is also called gikilite. Then manganese is there, so MnTiO3. Okay, when manganese is introduced, so it is called pyrophenite. It is called as pyrophenite. See, these are different terms. Okay, where the solid solution can be made. So at high temperature, you can see the third solid solution series exists between ilmenite and hematite. Okay, at high temperature, if you make one more solid solution comes between ilmenite and hematite. What is hematite? Fe2O3, like this. So this is what, and this hematite is nothing but red streak. Okay, so ilmenite has a black streak and hematite has a red streak. This thing, you know, hematite ore you have done. And this is what, and it has but this has no magnetic. Ilmenite, okay, they don't have magnetic, it has not magnetic property, but hematite has some magnetic, because iron is there. But ilmenite is not having magnetic property. Cleavage also is no cleavage for this ilmenite. Diaffinity is opaque, it is the opaque. Okay, so that it doesn't have diaffinity. Hardness, again you can see, hardness of ilmenite comes to be around 5.5 to 6. So they are hard in nature, ilmenites. Okay, and specific gravity is 4.7 to 4.8 specific gravity. Okay, this is what some of the properties of ilmenites. Okay, and you can see the alloys are used to manufacture wide variety of high performance parts. So whatever the alloys is been got from these ilmenites, so prepared from these ilmenites, they are used for the preparation of manufacturing of wide variety of high performance parts. Okay, so what are the parts? Like you can see aircraft parts. So in aircraft, you can see some parts are made, that is been made from the alloys from the ilmenites. Okay, so that it has been used. Then artificial joint for humans, artificial joints in humans. Okay, so in human being there is artificial joints, leg joint, hand joint, so many things comes in medical field. So that joints are also made from these alloys of these ilmenites. Okay, that is one, that is there. Then sporting equipments. Okay, so if you see in sports, so many equipments in the sports are made up of these ilmenites alloys, like or some bicycle frames like this. Okay, so this is how you can use. And maximum 5% of the ilmenite is used to produce titanium metal. This is important. Okay, so a maximum 5% of ilmenite is used to produce the titanium metal. Okay, and you can see that to produce it is having white, to produce white highly refractive pigment. Okay, main thing for titanium is to produce white pigments, refractive pigments. This is important. Okay, and the pigments, whatever the white pigments is been produced here, white color and brightness, it is used in paint industry. Okay, and sometimes paper industries, they use these adhesives. In adhesive industries these use this. Then there is plastics, in plastics they use. Then toothpaste, in toothpaste, and sometimes food industry also they use this. Okay, white pigment drawn from the titanium. Okay, so this is how. And yes, and if you see the conchoidal to subconchoidal fracture it is having. So it's a geological term, conchoidal to subconchoidal fracture. Okay, so these ilmenites have conchoidal to subconchoidal fracture. Okay, this is a geological term, that is cuttings. Okay, and crystalline is trigonal system also, like hexagonal I said. So it crystallized to trigonal system, and it consists corundum structure also, alpha Al2O3 like structure. And here Fe plus 2, Fe plus 2 and Ti plus 4 ions. These two ions are there, Fe plus 2 and Ti plus 4 ions. Okay, and they occupy the alternating layers perpendicular to this trigonal axis. Okay, so this is, and this is paramagnetic in nature. This is very much important, paramagnetic. Okay, and in 1971, William Greger, okay, William Greger discovered the ilmenites. Okay, he discovered this ilmenites in 1971. Okay, this is a thing you have to keep in the mind. Okay, so whether the altered form of ilmenite is formed, like we have seen altered garnets and all, yes, definitely the altered, you can alter these ilmenites also. Altered form of ilmenites form mineral leucocene. It is going to give mineral leucoxene. Okay, so this is called, sometimes they ask you altered form of ilmenites, that is nothing but mineral leucocene. Okay, leucoxene. So this is altered. Okay, and I think this is more than sufficient. Okay, for this what you say ilmenite. Okay, yesterday we saw the magnetic property, today we have seen the what you say different of this another general properties of these ilmenites. Okay, and peroxides also, peroxides So this we have learned peroxides in the previous video of the magnetic property. So this has a general formula, as I said, it has general formula of AbO4. Okay, so where A is nothing but your A plus 2, okay, and B is nothing but your plus 4. This is important. Okay, divalent and tetravalent, this is what AB. And anions like O minus 2 will be there. Okay, anions. And face centered cubic lattice, it is having FCC, face centered cubic lattice, peroxides. Okay, and here the a cation, whatever the cation is there here, they are located at 8 corners of cube, located at 8 corners of cube. This is important. Okay, cations, 8 corners of cube it is located at 6 face centered cubic centered. Okay, yeah, 8 cube and O2 minus actually. So this is O minus 2. O minus 2 ions is located here in FCC, 6 faces. Okay, FCC, that is face centered cubic. Okay, and B, that is plus 3 plus 4, B cation, it is located at octahedral position. It is located at octahedral position, B plus 4. Okay, so here cation is located at 8 corners of the cube, and O minus 2 is located at the FCC, 6 FCC faces here, and B plus 4 is at the octahedral position, at the center of the cube. The best example of this perovskites is calcium titanium TiO3. This is what CaTiO3. Okay, this is the best example, where here A is nothing but Ca plus 2, and B is nothing but Ti plus 4, and C and O is nothing, is atom, anion is nothing but O minus 2. Okay, and simply it is made in very simple this way, like this only you can draw. Okay, like this, and you can see calcium, it is present, I said, 8 corners as we have discussed here. A plus 2 here I have written. So cation is located at the 8 corners of the cube, so this is a cation, that is Ca plus 2. Okay, next is what your O2 minus at the face center, that is 1 2 3 4 5 6, these are the 6. Okay, so this represents your O minus 2, so which is present at the 6 faces, face center. So I have 6 face, 1 2 3 4, front side, back side, 6 faces, O minus 2. It is clear. And finally you can see here, I will draw a star here. This is a star, and that star is nothing but at the mid of the body, that is your titanium, B, titanium plus 4, like this. Okay, so here B4 is octahedral position at the center of the body. Okay, center of the, located at the octahedral position at the center of the cube, so like this. Okay, so this is how the perovskite represents, like this. Okay, and it is used for solar system and all. Why? Because the titanium is the one which is going to move from each octahedral site, tetrahedral sites created by this calcium and the O2 minus. Okay, so this is how it becomes a little bit conduction in nature. Okay, okay. Now if you see the contribution here in this peroxides, okay, so we'll learn that also. So contribution of Ca plus 2, I will write here, contribution. Okay, contribution of Ca plus 2 located at 8 corners, which is located at the 8 corners. So how much it will be? 8 into 1 by 8, that is equal to 1. Okay, so you know that from second semester. Corners means how many? So 1 by 8 contribution will be there. So how many are there? 8 are there. So a 1 by, so that is contribution of calcium is 1. Next we will see then contribution of 1 titanium located, contribution of 1 Ti plus 4 located at center, that is equal to 1. Okay, so Ti flow located at 1 is, the contribution also is 1 here, only 1 is located at the center. And finally O minus 2. Okay, so O minus 2 located where? Face centered, so it is nothing but how many? 6 into 1 by, so what is this? 2. Okay, so that is the contribution at the face, that is nothing but 3. Okay, now if you combine this all three, how, what becomes? 1 is to 1 is to 3 we got. Okay, 1 is to 1 is to 3, that's why. So what the formula comes here, the formula also comes here. So CaTiO3, like this. Okay, contribution of calcium is 1, titanium is 1, O3 is minus oxide is 3, so like this. Okay, so this is how we get into this contribution here. Now if you see even the coordination number. Okay, so if you see the coordination number for titanium, so here, so titanium is we have to see how many it is been surrounded by the calcium or this one 1 2 3 4 5 6. So coordination number of titanium comes to be 6. Okay, you have to see that's required in 3D dimension, and even the coordination number of O minus 2 is 2. Okay, O minus 2 is a 2. So you have to see that, and the coordination number of Ca plus 2, if you see this one Ca, if you see another cube here, another cube this side, another cube this side, like this side. So if you see this like this 3D dimension, then the calcium is surrounded, the coordination number will be 12. Okay, the coordination number of Ca plus 2 will be 12, because one calcium is surrounded by 12 another units here. So when you compare these 3D dimensions, this one and another one cube here, one cube here, one cube front side cube, so 12 will be there. So like this. Okay, but titanium is always surrounded by 6. Okay, so you do it and it's the imaginary type of this. So coordination number of titanium becomes 6. O2 minus becomes 1. Okay, O2 minus becomes 1 here. So almost O2 minus becomes 2. Okay, a coordination number, and titanium 6, and that of your what you say your calcium, it is 12. So I think this is what about the peroxides. Okay, and the last, this is what is left is your magnetoplumbite. Okay, so in your syllabus that is kept is your magnetoplumbite, magnetoplum magnetoplumbite. So okay, this is what there is for the final this one. So what is this magnetoplumbite? Magnetoplumbite is also nothing but a mineral. So magnetoplumbite means lead. This is important. Okay, so Fe12O19, this is your magnetoplumbite, PbFe12O19, and its barium analog, if you see its barium analog. Okay, so its barium analog is your BaFe12O19. We call it as a BAM, like this, BAM. Okay, so its barium analog of magnetoplumbite is this one, barium, BaFe12O19. Okay, and this is important component of permanent magnets. This you have to keep in mind. It's an important component of permanent magnets. Okay, this magnetoplumbite, that's why it's called magnetoplumbite. And the structure of this is closely related to beta alumina. So we have learned beta alumina, that is 5 layered, 1 2 3 4 5, 1 2 3 4 5. Then second layer 1 2 3 4 5, that is third layer 1 2 3 4 5. Fourth layer is 1 2 3 4. Fifth layer has the oxide, missing oxide, like this, like this. Okay, so here like this. So this is having some missing here, like this. Like in beta alumina we have learned the same structure we are seeing in this magnetoplumbite, where the fifth layer is having some missing some space will be there. Okay, where the ions will be flown in superionic nature, and that's why it's helpful for the conduction. So like this. Okay, so that's why this has the same structure like beta alumina, that is your NaAl11O17. Okay, aluminium O17, like this. Okay, so this is a beta alumina, sodium beta alumina, and it has same similar structure, 5 layer repeated axis of close packed. Okay, fifth close packed here, and 4 layers contain close packed oxide layer. This 1 2 3 4, this 4 layer 1 2 3 4, they contains closed packed O minus 2 layer, oxide layer, closed packed oxide layer. And as such we seen in the beta alumina. And the fifth layer here contains, here fifth layer, the space I have, they contains 3/4 of oxide ions with the large divalent ion. Okay, so they are going to contain here now Pb plus 2 and Ba plus 2. Okay, like this. So Pb plus 2, this will be there here in the fifth layer. Okay, it is moving here, Pb plus 2 or Ba plus 2, like this, inside this. Okay, what is that? O2 minus tag. So like this it is present here. Okay, in there it will was sodium, this will be, but here it is Pb plus 2 and Ba plus 2. Okay, so this with large divalent ions will be it will be there in these spaces. Okay, and the magnetic structure of BAM, barium magnetoplumbite, the here, so complex is because of Fe plus 3. Okay, because of this this has the magnetic property here. Okay, and this Fe plus 3, they occupy 5 sets of crystallographic sites. Okay, Fe plus 3, they are going to occupy the 5 sets of the crystallographic sites here, and the net effect is that, so BaFe12O19. Okay, and this is what the net effect is, that this 8 Fe plus 3, 8 in this 8 Fe plus 3 ions have spin oriented in one direction, 8 Fe plus 3 ion spin is oriented in one direction. Okay, and remaining 4 and remaining 4, 8, 9, 10, 11, 12. So remaining 4, so what happens here? So here the remaining 4 are anti-parallel. See here, are anti-parallel spin, okay, and giving resultant of 4 Fe plus 3 ions. Magnetic property of 4 Fe plus 3 ions with me value 20 Bohr magneton. This is what about magnetoplumbite. That's why they are very permanent magnets. So with the resultant of 4 remaining, okay, out of 12, 8 will be have the spin oriented in one direction. 4 will have anti-parallel to this. That means they cancels. 1, 2, 3, 4, 5, 6, 7, 8. If it is plus here like this, so 1, 2, 3, 4 will have the anti-parallel. So this 4 cancels. How much remained? 4. So net magnetic moment will be of 4 Fe plus 3 ions, and that comes to the value of 20 Bohr magneton. See, okay. And this is what about the magnetoplumbite magnetic properties. So same thing here, and that's what I think this is more than sufficient for this today's video. So in today's video we have completed our Illemnites, which was in the previous video we have started this Illemnites magnetic property. Today we went for the some of the general information of Illemnites, general information of perovskites with structures, okay. Structure also, that is important. If it's asked you write down the structure, magnetic property we have learned a very complicated magnetic property, they will not ask of this, okay. And finally we have go for magnetoplumbite. So short notes, this thing you have to write this much is more than sufficient as a short notes, okay. So this is what we have completed, one of the magnetic properties of the syllabus, or one part, okay. In the next video we'll go for another part, final part of the magnetic property, that is your ferromagnetic, then ferromagnetic material, ferromagnetic material, okay, dielectric material, something is there of the last point of the magnetic property. So if we complete in the next video, so last concept of unit 4 is left, that is your optical properties, okay. So once we complete this optical properties, the unit 4 will be 100% completed, okay. So I think another 3 videos we are going to complete the 100% of your unit 4. Thank you.